Hey class, Mr. M here with another in a series of videos to support what we do in class. This one is continuing our discussion about circles. Here you see our agenda items. We're going to talk about sectors and arcs in two different ways for each of them. We've already talked about sector area in class through a couple of examples, but I want to formalize that a little bit. We'll also talk about sector measure, and there's a difference between measure and length and area. And, whoops, there's a typo here. That should be arc length. My mistake. And we'll also talk about arcs in two different ways. The measure of an arc and the length of an arc. So, one of the key ideas here is that you measure something in degrees and you actually find its size, right, how long or how big it is in terms of units like centimeters or feet or square inches or what have you, right? So measure in degrees and length and area in normal measurement units. So one of the other key ideas here is the idea of a proportion. In fact, when you were first taught fractions way back in elementary school, you learned fractions more than likely, in something looking like parts of circles, right? This is, half of a circle right here shaded in. That's representing 1/2 or what have you. So circles, even in more advanced scenarios, basically deal with the same idea. The part that we want is usually what we're looking for. The whole part is going to be some idea about circles which we've already developed using pi r squared or 2 pi r or some other formula which I hope makes sense to you in terms of the actual shape a circle contains. And because it's a fraction, because we're going to be working with fractions, the idea of proportions will come up a lot as well. So when you think about trigonometry and similarity, all those concepts are held together here within the idea of a circle. So let's dive in. Sector measure. So what's a sector? We've already talked about that in the previous video as well as in class. A sector is like a slice, sort of like a pizza. Or if you remember the last video, a lot of people kind of took to the fact that these purple things were like onions. So here the onions have gone kind of bad. They're sort of lighter colored, but they're still onions. And the sector here is just the slice of the circle. It's not the whole circle, but it's a section of the circle. So we measure a sector, right? We're not finding its area, but its measure is simply the same number as the number of degrees that opens up in the middle or central angle to make it. So for example, if this central angle is 70 degrees, then we can say that this sector, this entire sector, also represents 70 degrees of the circle. Not 70%, but 70 degrees. So 70 degrees out of the total of 360. So 70 degrees is the sector area. Sorry, sector measure. I shouldn't be mixing those up. It's the sector measure. In contrast to the sector area, so let's look at sector area next. Sector measure, it's just the central angle. Whatever that angle is in the middle, that's the sector measure as well. Sector area. Here's an example. Find the area of sector APB, or this purple space. So, how does proportions fit into this? Well, let's deal with what we know, right? The basic idea of proportions is part over whole, right? You don't have to write that out every time. I just want you to keep that in the back of your mind. So what part do we know? We know we have 58 degrees of the circle that we're being asked about. I should try to color code this. 58 degrees is purple. That's the part that we want. The entire circle, right? The entire circle is that entire area, which I'll do in this brown color, right? So this entire area, including the purple, is 360 degrees of rotation. So 58 degrees is part, 360 is the whole circle. We all know that thanks to the Babylonians. And that fraction is going to be equivalent to, if we set it up properly, the same idea. So what represents the whole? Well, the entire circle, 360 degrees, is literally all of this space here in brown. All of that space is the entire area, pi times 6, which is our radius, squared, right? What is the area that we are looking for? We don't know. That's the question. So notice the 58 matches with the area, 58 degrees matches with the area, the 360 degrees matches with the pi 6 squared. And now we're ready for some simple arithmetic. So to make sense of this problem, I encourage you to not just cross multiply right away. Instead, just so we have an idea of what reasonableness will be in terms of an answer, I'm going to replace pi 6 squared with what it really is, and that's 113.1 approximately. Well, what does that represent? Well, look at the colors here, and in terms of the formula that it came from, it's the area of the entire circle. So our answer of A must be less than 113. And in fact, if you look at the circle and the sector, It's got to be a lot less than 113, because not much of it, relatively speaking, is filled in, right? A lot less than even a quarter is filled in if it's 58 degrees, right? So it's going to be a lot less than 113. In fact, it's going to be 58 over 3/60th less. So how do we do that? Once it's in this position, it'd be wise to cross multiply, just because that's something most people are comfortable with. So when you multiply pi 6 squared, or 113 times 58, you will get a number I had. 58 will give you a big number. It's going to be 6,559.6 approximately, but that's going to equal 360 degrees times our area. Divide by 360, and voila, you have the area. The area is merely, dividing by 360, 18.22 approximately. 18.22 square centimeters, y squared, because we were finding area. And there it is. A lot less than 113. The whole thing is 113. This purple space we have now established is 18.22. So physically that matches with our intuition, and our numbers seem to back it up. So that brings us to this formula. If you like writing formulas down, you're more than welcome to. I think it's better to understand, but more power to you. So oftentimes in textbooks you will see this formula right here. Area is equal to the central angle over 360 times pi r squared. Right? Fine. Great. You can use it. There's the area of a circle. There's the fraction that you want. I'm a big fan of that formula in some cases. However, if you're more of a person who likes to understand things and really deal with the proportion and similarity, this is the exact same formula. You can rearrange it for yourself and see, but this formula kind of shows you the idea about part on top over the whole thing on bottom, right? On tops you got the areas, and on bottoms you have the entire thing, which is 360, or the entire area. Alright, let's move on to arcs. What is an arc? Remember, an arc is part of the curvy part of a circle. So this right here is an arc. I should label this actually, because I've neglected to. I'll call this A, and I'll call this, very original here, B. Okay, arc measure can be quite complicated. Alright, at first though it's quite simple, but as it gets complicated, which we'll see next week, you want to be careful. Here's the important part. The arc measure, which is again in degrees, measures are in degrees, areas and lengths are in units. Measure of an arc in degrees is equal to the central angle measure. Basically use common sense. In other words, if this is, let's say, 25 degrees of opening right here, if these two radii cross at 25 degree angles, that means this arc here in red, this arc is going to be 25 degrees as well, which should make sense. In fact, it'll make very clear sense if I do 90 degrees. So if this is the center of the circle, again, here's the important part. This has to be the central angle. If it's not, then nothing I'm saying is going to make any sense whatsoever. It has to be the central angle, which at first it will be. So there's the, I'm going to draw a 90-degree angle here, roughly. A little bit difficult because I don't think this is exactly the middle of the circle, but that's about 90 degrees. It's not perfect, sorry. But anyway, there's about 90 degrees. Well, if that's 90 degrees, then this also here in blue, arc AC, must also be 90 degrees, which should make sense, because that's a fourth of the way around, right? So that would be 360, and that's the whole thing. So the arc measure in the middle is the same as the arc measure, the angle in the middle is the same as the arc measure on the circumference of the circle. So just to preview what we're going to be talking about next week, keep in mind that the arc that I'm about to draw also sort of crosses or subtends, as we'll use next week. It also sort of subtends the same arc. Notice that the red curve, AB, is still 25 degrees. I have not changed it. And yet, this green angle here that I've made is not 25 degrees. It is in fact much less than 25 degrees. It's narrower. Why is it not the same? Why is this less than 25? Again, it's not in the middle. It's got to be in the middle for that to work. Alright, so enough about arc measure. It can be measured in degrees. Let's talk about actually finding an arc length. The good thing is, it's just like it is for area of a sector, except instead of using the area of the inside part, we're just going to use the circumference, the total length of the outside part. So here's an example of a question you might see. Let me give myself some more room here. Find the length of arc AB. Okay, well that's the red part that I've outlined here. That's the length that we're wanting to find. We already know that it is 42 degrees of rotation, right? That's its arc measure. We want its length. So, just like before, I'm going to set up a proportion. The entire circle is 360 degrees in rotation, right? That's an entire circle. The part that we want is merely 42 degrees of it. Fair enough. That proportion must be equal to the part over whole proportion, not in terms of degrees, but in terms of linear units. So 42, which is the part that we want, well, I don't know what that is because that's what's being asked about. We don't know how long this is. I'm calling that L for length, right? We don't know how long that is. But what I do know is that the entire length all the way around the circle has a special name. Aha! 360 is degrees, but the whole length all across the circle is pi times diameter, and that is the circumference. So this should look very familiar. That's the circumference, right? So in this case, it's pi times diameter. Well, if the radius is 3, then the diameter, naturally, is 6. So pi times 6. Oops, pi times 6. All right, so part over whole, same thing is held true. I'm going to go ahead and find out what 6 pi or the circumference is, again, so we know if our answer is reasonable or not. I highly advise you do that. 6 pi is 18.84. So all the way around the edge of the circle is 18.84 inches in this case. So our final answer must be significantly less than that. Why? Look how much shorter the red thing is compared to the green. So that will be our basic intuition. So once again, now that we're in a position that we have a reasonable answer to compare against, I'm going to cross multiply, which will give me 360L equals something that I had, but I accidentally cleared my calculator. Let's see, 42, some weird number like 791.68. Not important at the moment because that is 360L. One mere L, the length of our arc is, whoops, I don't know why I put a degree symbol there. Crazy things you do. I do, I guess. Divided by 360, that is degrees, but it's going to cancel out anyway. And that divided by 360 gives us a final arc length, drum roll please, of L equals 2.199 or 2.2. So this is 2.2 inches long. The red thing is 2.2 inches long. The whole thing all the way around is the circumference, right? We can do that in our sleep by now. That's 18.84 pi times diameter. Just 42 degrees of it is 2.2 inches. Which makes sense, right? Not a whole lot. Once again, there's a formula. Here it is. Use it if you want to. I like it sometimes, but it's better to understand. If you're a math pro, right? Study it, use it, recognize that this green thing is very familiar to you, and this fraction right here is just part over whole, the same kind of fraction idea you have dealt with since you were in 3rd grade. But if you have trouble with this kind of thing, it may help you to visualize it as a proportion. On top are the parts, on bottoms are the wholes. In this case, it's the circumference. That's 13 minutes, a long time, and I will see you on Monday. Hope this helps.